Okay, so here's the story. I'm going to have these two pieces. Let's see if we can put them together. Okay. So the idea is going to be this. So we're going to have to glue a few pieces together to make everything work. But so we're going to have this. We're going to randomly choose a node. This is pi sub n. This is the probability that it is part of a finite component of size n. So that's sort of this represented here. And then, so this is, could be all sorts of sizes. P sub k, this is the probability that it has k edges, right? So this is a little local thing about our node. This is a non-local piece. And what we start to say is, well, okay, we could tie some things together. So the probability that, right, we're going to take this and expand one step. We're going to say, what's the probability that we have n nodes if we think about choosing a node? It's going to have degree k, so with some probability p sub k. And so given that it has k friends, then we run out along each one, and then we use this next thing, which is the probability that that hits a node that is part of a finite component of size whatever. So it's take a little while to work together, but we, so it's a Markov property, a random recursive relationship. So pi n, rho n, and p sub k. So we're going to tie this probability that we have n friends to the row probabilities, right? Which is the probability that running along an edge leads to a finite component of size, in this case n sub 2, n sub 3, n sub 1. And we're going to say, okay, we should be able to establish a relationship which says that the probability that we're part of, we have n friends, is the probability that we have k friends, probability that we're in a component of size n, a finite component of size n, is equal to the probability that we have k friends, and that those friends, when we look at the components, the finite components they're part of, and we add them up, and then we add 1 for ourselves. So that's what this is, 1 plus the sum from I equals 1 to k of these little, these components that we're leading to. That sums up to n. Yes?
So you're assuming that there's no overlap between the components?
Yeah. So, really important thing, yeah. What we're doing is we're avoiding the giant component where there are loops. All of this will be about the outside where everything is a pure branching structure. So, we'll see later on you can actually do all of that, but all of this work assumes a pure branching structure, which is true for finite pieces. So this is a finite component, right? It's got 371 nodes in it, whatever it is. There will be, in an arbitrarily large random network, there will be no loops. So you can do it. So it's kind of a coward's way out, right? We're just like, well, loops are hard, so let's go over to the things that are really easy. We'll work all of them out, and then we'll say 1 minus all the stuff we know is that. What's kind of amazing is that, and it took a number of years to get there, but you can actually, with a different approach, go right into the giant component and really talk about it. It's pretty fantastic, actually. So, how do we feel about that? Delicious. So, really important point. Pure branching structures. Only finite parts of this thing. And if there's a giant component, we just sort of step away. Okay, so this is a thing that connects, really says pi of n is going to be related to p of k and rho, right? Pi is going to be related to p and rho. This just has to be the case. Just with one step. We could do one more step, which would be kind of crazy. We could say, oh, this thing has some degree, and then we could, do more out here. But we don't need to do any more steps because, and everything would still work. It's just that we only need to do one step because of randomness, right? That this is all going to be going on. Okay, so it's a very important picture there, so the idea is this is 1, 2, 3, and then there's ... around a k. That's the idea there. So you want to start thinking, okay, I could be part of 370, a cluster, a finite component of 371 nodes It could be that I have one friend who's part of a subcomponent of 370 plus me. I could have two friends, and then you have to think of all the ways you can add up to 370, right? So it could be 1, 360. So you do all of those, and you have to do all the probabilities, and then you can have 3 friends, and then you have to break all of those up, right? So this is starting to look a little hairy, right? Yeah. Or you could have 370 friends, and they have no other friends. You could be the cult leader, right? So you can enumerate through all of those things, right? So, but what that would mean for the cult leader thing is you choose 370 friends, or you're sampling from this thing and you get 370 and you say, okay, and then each time you go out here, when you sample, you have no other friends, yeah? So you hit a node who has no other friends. That's a structure that, if you have a non-zero probability of 370 and a non-zero probability of nodes having one friend, you'd get it out in your big calculating mess, right? So that's a lot of bookkeeping, right? That's a lot of beans and stuff that you have to put in, like things, like it's just a lot. So we don't want to do all the bean stuff. We would like nice little beautiful things, yeah. So we will clamber our way towards beautiful things. Okay, so here's the one we can really, so the problem with this is tells you what pi is in terms of rho and p sub k, right? So it's going to tell you about, it's going to make an equation when we get to it that involves pi somehow equals, not equals, but I'm just saying pi is going to be somehow given to us in terms of p and rho. But so there's no way to there are too many things in there, right? We can't solve anything. But this next one, we can, right? So again, we know P sub k and R sub k. They're things that are handed to us, right? P sub k is handed to us. Here is this degree distribution. We can compute R, which is the number of other friends a node has. That comes from P sub k. So we have those pieces. We don't know about rho and pi. We're trying to get those things. And right? So if we have rho and pi, if we have pi sub n, then we know what's probably that you are part of a component of 1, 2, 3, that's a full solution to this thing. So it's, often we'll be interested in the average size of those things, but actually we're really going for the full, buffet, shall we say, the smorgasbord. Okay, so this one, and I haven't written down the equations, but we can just sort of hopefully see that this feels like it should be solvable. So rho of n is probably that you run along an edge and it leads to a finite component of n nodes, right? And R of k is this local thing, which is again the probability that you hit a node that has k friends. So we're going to use those. So this guy should be able to relate to this one. And there's a simpler kind of recursive structure. Here's our rho. We're going to expand it. What's the probability that we have n friends? Well, it's probably that the node that we hit has k friends, k other friends, I should say, k plus 1 total, has k other friends, and they are part of finite components of size 1, 2, 3, right? n1, n2, n3 to nk. And when we sum them up and we add 1 for the friend we hit, we get n, right? This n is this n. Okay, so we want to say what's probably that we have n nodes in our finite component. It's probably that we hit a node, again, that has k other friends. We get 1 for this one. And when we sum up all of our k other friends' component sizes, we get n. No. I'm literally saying the meme where the GIF that has the shade goes across the top of the buildings. Shade goes like that. So I'm not sure if that's the right thing my brain should bring up right now, but I feel like I'm being memed. Should hold up things with memes on them to, yeah. It's quite juicy. No? Delicious. So rho connects through this R sub k to more rows. So that's a big soup, but it only has rows and R's in it. So it feels like we should be able to disentangle that thing. Maybe? Maybe. All right, we can come back to that picture. All right, so let's see if we can glue these things together. Okay, exciting. All right. So here we're writing down the generating functions, right, for these component sizes. Again, just we have a straight up definition for generating functions. Whatever our sequence is, whatever our probability distribution is, we just write it out. We stick x's with the right power next to everything and sum it up. That's it. Okay. So this is this thing that I was talking about in the 2 slides ago. F pi evaluated at 1, right, which is the sum, right? If you set 1 here, it's the sum of all of these probabilities, pi 1, pi 2, pi 3. Pi 0 has to be 0, right? You can't hit a node that has to be a component of size at least 1 because it's there. This is the probability that a node belongs to a finite component, right? We're scared people. We're not going to go near the giant component. It's got loops. There are here be loops on the map. Okay, so if we could figure out this generating function, we don't have to unpack it all to get something useful. We can in fact just do this, right? 1 minus that generating function evaluated at 1 will give us the probability that this is the total probability that a randomly chosen node is part of a finite component. So 1 minus that is probably that it is part of an infinite component. Okay. This slide should burn up, I guess. That would be a nice effect. But anyway, yeah. Okay, so yeah, right. Maxwell Smart. Anyone ever watch that? It's from a long time ago. Okay, so get smart. Okay, so we're going to connect these things, and so we know these. We have this guy. That's, we know P, so we can determine this generating function. This one we figured out is the first derivative of this function divided by, again, the first derivative evaluated at 1. So that's a story we have already. These ones somehow will be, in principle, derivable from f of p. So everything should come back to here somehow. We may not be able to extract it all, but at least we can get some closed form things.